All right, so we're going to go over the review for chapter 1.6 through 1.8. So let's start with the vocabulary. So all of these that have to do with the x coordinate would be your independent variable, which would make your y coordinate your dependent variable. Your y variable, your dependent variable depends on your independent variable. So the independent variable is subject to change, and the dependent variable will only change if you increase or decrease the independent variable. So your domain is your x, making your y your range. Your input is your x. Once again, you can't have output unless you have your input. And then f of x is equivalent to y. So we're going to put that in that column. All right, so our next one, drag an x over the representation that does not belong. So I'm going to start by just looking at this first ordered pair in all of them to see if they match. So we have 4, 5. Looking at the mapping, 4 is pointing at 5, so that one's the same. 4, 5 is paired in the table, and 4, 5 is on the graph. So let's look at 2, -3. So I'm going to come down here. 2 is pointing at -3. 2 and -3 pair on the table, and 2, -3 is on the graph. -3, 5. We have -3, 5, -3, 5, -3, 5. So far, everything's lining up. And now -1, -1. This should be the one to help us eliminate which one does not represent, which one does not belong. So -1, -1. In our mapping, they're pointing at each other, x, y in the table. But instead of -1, -1, the graph has -1, 1. So the graph does not belong. All right, so they gave us a relation. We need to express it as a table, graph, and a mapping, and then state the domain and the range. So the easiest one to start with is putting it into the table. So we have to keep them paired up together in the table. The table is just a way of organizing ordered pairs. It does not matter if they're increasing or decreasing in a table. I'm going to drag them onto my graph. So I have -3, -3. So I'm going to go over 1, 2, 3, and then down 3. So it lines up with both the x and y axis at -3. Our next one is -1, 1. And I'm going to zoom in for this one to make it a little bit easier. So that way we can be more accurate. There we go. And now we have -1, 1, 0, 2, 2, -3, and 2, 3. All right, so now we're going to put it into our mapping. So this is where it matters about if it's an increasing order and not to repeat anything. So looking at our x values, the smallest one is -3, and a -1, and a 0, and then we're only going to put 2 once because we do not want to repeat them. This is just the possible x values for this relation. All right, now looking at the y, same thing, least to greatest. So -3, we only need to write it once, even though it happens twice. 1, 2, and 3. So I got all those from the table. So now we need to make sure that they are pointing at their correct partner. And remember, this is really useful for determining if it's a function or not, because you can see if an input has more than one output. So -3 needs to point at -3. -1 needs to point at 1. 0 needs to point at 2. I'm getting this just directly from the table or from the ordered pairs if I wanted to scroll back up. And we have 2, -3. So I just need to readjust this. There we go. And then we have 2, 3. So since we have an input value, a member of the domain that is pointing at two members of the range, even though it's not asking you, I'm just bringing it up, this would not be a function. All right, so let's look at our domain and our range. Since this is a discrete function, meaning that we don't have any continuous points between, or data between the points, they're just very distinct, discrete points. We're just going to list what we did in our mapping. So whenever you do it in increasing order in your mapping, it makes it easier to do your domain and your range. All right, let's move on. All righty, so we are going to write the ordered pairs for the mapping. So it's just understanding that the X is pointing at its corresponding Y value, which means that they are written as ordered pairs together. So we have -2 is pointing at 4. And we have -1 is pointing at 4 as well. We have 0 pointing at 6. We have 1 pointing at 8. And we have 2 pointing at 8. So even though it doesn't ask us again, this would be a function because two inputs can share the same output, but one input can't be paired with more than one output. All right, so we're going to do the domain and the range from the tables. So we're looking at our X values for our domain. We have 2, 2, and 3. Remember, we do not need to repeat. So our domain here is just going to be 2, 3. It's an increasing order for our range. Once again, we want to make sure it's an increasing order. So we have -4, -1, 0. All right, for our domain, we don't have any repeats. Make sure it's an increasing order. So the smallest value would be -2, -1, -3, -2, then -1. And then same with our range. And make sure you're using these pinched brackets. That is our set symbol. So it's saying this is our set of values for the domain. If you use parentheses, then it's not going to represent the same thing. And then in increasing order. All right, one more. Domain 33, 35, 36. That was easy. It was already in increasing order. And for our range, remember, no repeats. So 8, and then we only have to type 10 once. So now we're going to be getting our domain and range from discrete graphs. So this one is just the same thing. For the domain, I'm going to look for everywhere these points line up with the x-axis. I could also technically write down the ordered pairs for all of these and then just collect the data from those, but I'm just going to show you how I do it. So we can see here that they're counting up by 2. So this is 2, 4, 6, 8, 10. Our first point lines up with the x-axis at 2. And since we're going from left to right, it's going to be putting it in increasing order. Halfway between 4 and 6 will be a 5. This point lines up at 8. And then this last point would be between 10 and 12, so it's 11. Now for the range, we're going to use the same process, but instead of looking left and right, we're going to go bottom to top. So we're going along the y-axis. So the first place that a point lines up with the y-axis is at -4. And then, oh, hold on. This is not increasing the same way as the x-axis. So here you can see that they're actually going up by 1 unit. So that would be a -3. And then a -1. And be careful about that. I mean, it just got me. 1, and then the other point lines up at 3. All right, we're gonna do the same thing over here. Our first points, they line up with the same x, so we do not need to repeat it. That is a -1, 2, 3, 4, 5. Next point lines up with -2. So if you watch my cursor, it should help. And then the last point goes to 2. So we know that our smallest value would be -5 and our largest value would be 2. So like technically we wouldn't even need this part of the graph. So it really just helps us give us our boundaries for these functions. Excuse me, this one's not a function, for our relations. All right, domain, now we're on range. So that's once again along the y-axis, bottom to top. So the first points the lowest points line up at -4, and then at 1, and then at 3. All right, so here we are going to be reading a qualitative graph. So basically what it means in a real world situation with our increases, decreases, and our like no movement. So our X is our time and our Y is our distance from home. Once again, remember our Y is dependent on X. You're not going to be able to travel if time is not passing. So if you were to stop the clock, then you wouldn't be traveling anymore. So time has to pass in order for you to make changes to your distance. So right here, we went from 0, 0. So that means at 0 time, you are 0, whatever units you're using to measure from home. That means you're at home. So as time is increasing, the distance is getting larger. So that means you're traveling farther from home. Now there's this little flat line here. So you notice that time is still passing, but we are not increasing our distance from home. So this would mean that we're not traveling. And then we have that flat line over here again, and that would mean the same thing. So this is a little bit steeper than before, but we're still increasing on that y-axis. So that means that our distance from home is getting farther. All right, so wherever you're leaving home for, this looks like that's where you're staying there because time's passing and your distance from home is not changing. All right, so here we can see that we're going lower on the y-axis, which means that the distance from home is getting smaller. So you're traveling closer to home. Once again, this part right here represents not traveling. Say maybe stops a stop sign even. I don't know what the time measurement's in, or you stop to talk to a friend. And then once again, you are slowly going down that y-axis as that line's decreasing. So you're traveling closer to home. And then right here where you're touching, that would mean that you're at home again. That would be 0 distance from home means you're at home. All right, let's look at some more qualitative graphs. So a tomato plant grows taller at a steady pace. So that means that it's not going to get steeper or it's not going to flatline or anything. So this one right here, graph C, you notice that it's going at a steady pace, or we talked about it now a little bit, it's linear. So a tomato plant grows quickly at first, remains a constant height during a dry spell, then grows at a steady pace. So this one right here shows it's growing and then it immediately starts growing faster. Here it's growing and then this flat line means that the height's not changing. So that means that this one's going to be graph B. And then you can see that it still remains to grow after that dry spell. All right, and then the last one, let's make sure it makes sense and don't just type graph A. A tomato plant grows at a slow pace, then grows rapidly with more sun and water. So it's more of a gradual, we're not going too high up. That's a long time passing. We didn't get very far. And then shorter amount of time passes and we spike up that y-axis so the height gets taller faster. So that means that graph A does make sense for the scenario. All right, this one, obviously, you can do on your own. We're not going to do that one together. All right, so drag a checkered X under each relation that represents a function. So there's a couple ways you can do this. I'm going to do this by making a mapping, just to make life a little bit easier. So let's see here. I'm going to write the ordered pairs on my little board, and then I will show you. All right, so for our mapping, I'm going to have my domain values. I'm going to kind of make a little area to keep them nice and neat, and my range. So remember, domain, range, or look at it as like doctor to go in order. So looking at my X values, because those are my members of my domain, I'm going to go from least to greatest. So 5, 6, 7. There are no repeats. If there were, I'd only write it once. And now I'm looking at my range. That would be the ones that are not dotted or underlined, and we'll go in increasing order. So 2, 3, 4. 7 needs to point at 4. 6 needs to point at 3. And 5 needs to point at 2. So each of our members of our domain only point at one member of the range, or each input only produces one output. So this will be a function. All right, let's look at our next one. So we got a domain in our range. So looking at our X values for our domain, we have a repeat. So we're only going to write 12, and then we're going to write 15 one time. And then looking at our range, we have no repeats. We're going to go from least to greatest. So -2, 0, 3. So 15 is going to point at 0. 12 is going to point at 3. And 15 is going to point also at -2. So this right here, because 15 is paired with more than one output, makes this a non-function. All right, let's look at our next one. All right, domain range. I'm just going to shortcut it this time. All right, so we got 0, 2, and 0. So we're only going to write 0 once and 2 once. And then we've got 1, 1, and 3. So we're just going to write 1 and 3. So 0 points at 1, 2 points at 1, which so far that's okay. Two domains can share an output. It's just one domain cannot have more than one output. But because the 0 also points at 3, this does make it a non-function. So that one will be an X. All right, here's the last one we're going to do from ordered pairs. However, there are many other ways to determine functions. So we have our X values for our domain. We do have a repeat there, but let's start with the smallest. We got -3, 0, and then we're only going to write 4 once. And then for our range, we have no repeats, and we go -2, 1, 2, and 3. So 4 is going to point at 1, -3 is going to point at 2, 0 is going to point at 3, and then 4 is also going to point at -2, so that there makes it a non-function. So honestly, this one's easier than the last slide. They're already mapped for you. So we're just looking to see if an input has more than one output. So here, 5 is pointing at 2 and 4. That makes it a non-function. All right, so here, -1 and 2 are both pointing at 4, but that's okay. So think of it as like your favorite color. I can't have two favorite colors, but you and I can have the same favorite color. So these two guys can share one. It's just one can't be paired with more than one. So this is still a function. All right, and the last one you can see here that -2 is pointing at 13 and 15. So that makes it a non-function. All right, so for this one, I would also like to use a mapping. It will make it a lot easier. So for our first one, domain, we're looking at our X values, no repeats. So there are, or we don't want to repeat, and there are repeats. The smallest one we have is -2. We only need to write it once. Then we have -1 and then 0. And for R, we have -1 and 1. Now this one's kind of like a trick question. So you'll find out what I'm talking about. So -2 is supposed to point at 1. -1 needs to point at -1. 0 needs to point at 1. -1 needs to point at well, that's still the same one. That is not an input being paired with two different outputs. It just so happens they repeat it because I think they're trying to like catch people who just look to see if these repeat. So I don't know. Anyways, and then -2 needs to point at 1. Once again, that one was already there. So really, those are just repeats in the table. So since each input's only paired with one output, this would be a function. All right, let's go to our next one. All right, least to greatest for our domain. So we've got -6, 0, 2, 3, and 5. And then we've got our range. We have a repeat, only write it once, -3, 0, 1, 4. And let's draw our arrows to see how they all interconnect. So we have 5 pointing at 0. We have 2 pointing at -3. -6 is pointing at 1. 3 is pointing at -3. And 0 is pointing at 4. So remember, they can share an output. They just can't have more than one output themselves. So this is a function. All right, last one we'll do from a table. All right, so increasing order, -6, -1, 0, 1, 6. Same with our range, -2, -1, 2, 3, 6. So 6 is pointing at 2, 1 is pointing at -1, 0 is pointing at 3, -1 is pointing at 6, and -6 is pointing at -2. Each member of the domain is only pointing at one member of the range. It is also a function. So if you thought you were wrong because all of them were functions, don't doubt yourself. Oops. All right, for this one, I made myself a vertical line. Hopefully that'll help us determine if they are functions or not. So I'm going to drag this across, and you'll see that there is no point where this line that I'm dragging is touching this graph more than once at a time. So even though it's very steep, you can see that as I'm moving, it's touching different parts of the line. That means that this first one passes the vertical line test. It is a function. All right, so the second one, we start to drag it, and immediately you would see that it is not a function. It is touching here as well as here. So that means that an input is sharing two different outputs, so that is a non-function. All right, and last but not least, we drag it across, and once again, immediately, it is touching at two different places. This is not a function. It does not pass the vertical line test. All right. Oh, I'm gonna copy and paste my line so I can use it again over here. Okay. So once again, vertical line test. So we're dragging it, and there you go. Already it's touching it twice. So that means that one, which graph represents a function, is not a function. All right. Dragging it immediately is touching two places. That is not a function. And this one, it is literally a vertical line. So that means it's only all touching vertically. So that's definitely not a function. And then as we drag here, we see that it's only touching in one spot all the way through. So that means that 4 is a function. All right, and for this one, let's see here. 0 is paired with 3 and 0 is paired with 6. So that is not a function. -7 is paired with 5 and -7 is paired with 1. So that's one input, two separate outputs, not a function. Here, 6 is paired with 2 and 6 is paired with -2. So that is not a function. And here, there are no inputs that have more than one output. So it is 4. All right, so looking at function notation, evaluate f of x equals 4x minus 2 for x equals 0 and 2. So in other words, x equals 0 and x equals 2. So the first one, they're saying that if I have an input of 0, meaning if my x is 0, so 4 times 0, we're just going to evaluate now, is 0, and then minus 2, and then 0 minus 2 is -2. So when you are asking, or excuse me, when x is 0, the corresponding y value is -2. So your input, your output. So this would be a function, because if you plug in 0, you will never get something different out. Each input will only have one output. All right, so let's do it again, and we're going to do it with an input of 2. So 4 times 2, we get 8. Minus 2, then 8 minus 2 is 6. So if you plugged in 2, 6 comes out. 6 is dependent on that 2 being there. All right, next one gets a little trickier. So evaluate g of x equals 2x squared minus 10. So this one says g of 3. So that means that we want to know what's the output if I plug 3 in. So order of operations, I need to apply that exponent first. So that's going to give me 2 times 9 minus 10. 2 times 9 is 18. Then 18 minus 10 gives us 8. And if you wanted to use your calculator for this one, that would be fine. You just got to make sure that when you plug it in, you're putting the parentheses just like I'm doing when I first plugged it in. So that way it helps with the order of operations. All right. Now, if I plug in -4, what's my output? So this -4 is in parentheses. So you're squaring the negative sign with it. So this is -4 times -4. So this becomes 2 times a positive 16 minus 10. 2 times 16 is 32 minus 10. And then when we finally finish simplifying it, we get 22. So y is 22 if you plug in -4 for x. All right, and I'm going to show my work for these, so give me one moment. I don't know why I said give me one moment because I paused it. Either way. All right, so I'm just going to show you the first two first. So we have h of 2. So when you plug it in, exponents first. So that 2 to the third power is 2 times 2 times 2, which is 8, minus 2 plus 7, working left to right. So 6 plus 7, 13. So if I have an input of 2, my output is 13. Now this one's only tricky because of that cube there. Think of this is a -1 times -1 times -1. So a -1 times a -1 would be +1, and then a +1 times another -1 would keep that negative. Even exponents will make it positive if you have a negative there, and it'll remain negative if it has an odd exponent. The other tricky part here is that as minus a -1, so remember subtracting is the same thing as adding the opposite. So like keep, add, opposite, so become +1. So for h of 2, we got 13. H of -1, we got 7. I'm actually going to walk through this one with you step by step in case the other ones were kind of confusing. So exponents first. 4 cubed is 4 times 4 times 4. So 4 times 4 is 16. And 16 times 4 is 64. So this becomes 64 minus, we don't need those parentheses. We don't have to change any opposites or anything. And then plus 7. So 64 minus 4 gives us 60. And then 60 plus 7, 67. So specifically when x is set as 4, or you have an input of 4, your y will be 67. All right, so now we're going to look at different qualities of these graphs. So this graph right here, it is a straight line. There's no change in how steep it is. That would make it linear. There is no x-intercept that we can see. And that would make sense here because you can't go into the negative side of dozens. You can't order a negative amount of something. So we would not end up having an x-intercept here. That would be real world. Y-intercepts, we do have one right here. It is 0. And if that's 200, this is 100. So between 0 and 100, it's going to be 50. 59, 50. So that means that before you order any shirts, your cost is $50. So I would think that would be something like shipping or a membership fee, something that you pay once and upfront. All right, let's look at where the graph is increasing. It is increasing for all values of x. So that's increasing at all points in time. So increasing for all, here we go. X is increasing for all real numbers. And at no point is it decreasing. So we're going to type NA, and that just means not applicable. It does not apply to this problem. All right, so let's look at that domain and range. First thing I'm doing is I'm going to go ahead and drag my X because that's what my domain is, and drag my Y because that's what my range is. So we want to know what is the smallest value of our domain. So we're looking from left to right. Well, we've got these arrows, which means that it is going to continuously keep increasing, which means we would essentially need to extend that x-axis. And remember, we talked about how numbers over here wouldn't make sense for our x value. So we're going to say that the smallest x value that we would have would be 0. So our x needs to be greater than or equal to 0. But there is no limitation to how many orders that you can make that we are made aware of. So that means that it would then also be less than infinity. Now for our y, we're looking bottom to top. So at no point in time are you going to be able to have a negative order cost. So for our y, we're just going to say that because this is increasing infinitely, that y just has to be less than infinity, and it also has to be greater than or equal to 0. From these arrows here really tell us that there's like an infinite number of options that go on and on and on. If it had a stopping point, we would see the boundaries a little bit clearer, but we also need to take into account this is a real world problem. So we know that what would make sense. Now, if this was just a regular graph and it was passing into one of the other quadrants and it had an arrow at the end, then we could say negative infinity. But like I said, because we have it in a real world context, we got to think about what values make sense for this problem. All right, so here we have a graph that has a curve. At one point it's decreasing and at another point it's increasing. So that means that it's definitely nonlinear. Linear would be a straight line. So it would be a constant increase or decrease. X-intercepts, we have 2 here. So our first one over here is touching right between -8 and -16. So that would make it -12, 0. And we have another one over here, halfway between 8 and 16. That would be a +12, 0. Right, and y-intercepts, we see that it's touching the y-axis at one spot. So if this is -8 and this right here would be -4, we're looking between them. That would be a 0, -6. All right, let's look at for when it's increasing. Remember that we want to know what it's increasing in terms of x because we're looking like left and right. So it starts to increase right here. That's where like it's going down, it stops, and then it begins to increase again. So it's increasing for values of x that are greater than 0. So where it lines up, like it says, focus on that x-axis. That tells us what we're comparing it to. So for all values that are greater than 0, it is increasing. It's not greater than or equal to because it's not increasing down here. This is where it begins to increase. Anything to the right, but not that actual point, it's increasing. And for decreasing, we have it's decreasing, it's decreasing, it's decreasing all the way up into 0. So x is decreasing when it is less than 0. All right, so let's look at the domain and the range. So our domain, once again, I'm going to drag that x, and then I'm going to drag that y. All right, so for our x, because we have these arrows and this parabola, which we haven't really used that word, sorry, this graph is going, it's like a U, is going to keep getting wider and wider and wider, meaning that there's no limitation to how far right and left it goes. So it is going to be greater than negative infinity, but it also has to be less than infinity. And remember, it's not or equal to, because you cannot be equal to something that we can't even define. We can't give a number for infinity. That's why we have the term, the concept of infinity. All right, and for our y, remember we're looking at how far down it goes and then how far up it can go. So the lowest that this graph is at that -6. So it's going to be greater than or equal to -6. Smaller, so it's next to each other. All right, but there is no limitation to how large the y is. So we could leave, we want to also include its boundary on the other side. So y would also need to be less than infinity. So basically, the way we're writing these are compound inequalities. You're saying, and they're the and ones, the intersection ones. So y has to be greater than or equal to -6, and it has to be less than infinity. So we have to be between these two things. All right. Once again, it is not just one straight continuous line that makes it nonlinear. Even though it looks like there's linear parts in it, the graph itself is not linear. There is an x-intercept right here where it touches. That would be a 3, 0. And we have a y-intercept. That would be 1, 2, 3, 4, 5, 6, 0. All right, so there's a couple places where this is increasing. We have when x is, let's see here. This is going to be a compound because we do have like a boundary, like from one side to the other. There's not like an arrow that keeps going on the other side. So this portion right here is increasing. So that's where it lines up at -3 and then it stops at 0. So it's when x is greater than 3, but also it is less than 0. But that's not the only place that it's increasing. It's also increasing over here. So this is a union symbol. It's showing that they both are places where it's increasing. You can use that, or you can just say and. We're not going to be too picky about that right now. And so also we have x is increasing here. So starting at 3. Wait, hold on. I made a mistake earlier. I wonder if I'll count that. That one should have been a -3 to 0. Okay. So this one's going to be greater than 3. So we're going to the right of 3. So that means we're larger than 3. But then it stops increasing at 6. So it also has to be less than 6 while it's increasing. Decreasing is going to be the same way. There's two places that it is decreasing. Is decreasing between -6 and -3. So x is greater than -6 and less than -3. And it's also decreasing between 0 and 3. So remember, you're looking at that x value of those coordinates. So x is going to be greater than 0, but also less than 3, where it is decreasing. So all values in between is where that decrease is happening. All right, very last one. We are doing the domain and range. So once again, x for our domain, y for our range. All right, so for our domain, we're looking for how far left and then right it goes. So the farthest left it goes is -6. And so all of our x values are to the right of that. So we're going to be greater than or equal to the smallest value for our domain. But we also need to be less than or equal to the largest value for the domain, which would be how far right we're going. So we're not using any infinity symbols here because, and I'm just going to make a copy of this one, because there are no arrows on the end. So there are clear start and stop points. All right, and for our range, we're going to look at how far down and how high it goes. So y is going to be greater than or equal to the lowest point it touches on the y-axis is 0. So we're going to be greater than or equal to 0. So you're going to be greater than or equal to your minimum. That's the smallest value. And then you're going to be less than or equal to the highest point that lines up with the y-axis, which is right here. And I believe that is 6. 1, 2, 3, 4, 5, 6. Yes. I'll take a copy of one. And there's the review.